Thank you, Yash, for the invitation. Thank you, everyone, for being here. So I'll be talking about my work over the last 2 to 3 years on computational ethics for autonomous systems. But first, overall, in my lab, we deal with a bunch of issues using formal methods. So computational ethics, which you will hear about here, these are the students who work on those questions. Distributed analog monitoring, temporal logic inference, learning temporal logic formulas from data. And I have a couple of projects with the FAA, the Federal Aviation Administration in the US, on the cyber physical security and integration of unpiloted aerial vehicles into the United States airspace. Hushal didn't send me a picture, so the cat is a stand-in for Hushal. All right, so, okay, so we all know autonomous cars are actually running in the US, especially in Arizona, where they are, Google has an autonomous taxi service, like actually running and operating without any safety drivers. And when developing autonomous systems, fully autonomous systems, whether it's a car, whether it's a robot in a nursing home, whether it's a robot in the elder care environment, etc., understandably, the first concern is safety. Is this thing safe, or perhaps more practically, under which conditions is it safe, right? And every time a Tesla or some such highly automated / autonomous car has an accident, it's very widely publicized, and for good reason. The question, organizations like the FAA are interested in certifying things and certifying safety, which raises the question of, okay, well, how do you develop an entire process around that, right? In order to finally allow some operator to fly their UAVs, for example. But safety is not enough. And what I will be discussing in this talk and what I've been working on is something beyond safety. When we are talking about autonomous robots, and I'll just use the generic word robots here, right? When we are talking about autonomous robots interacting with humans in our daily lives, in our environments, rather than in highly controlled environments like a factory, then beyond safety, we would want those robots to have a sense of ethics, because ethics govern more or less our daily interactions with each other, whether we have them explicitly in mind or not. And so to have a more natural interaction with these robots, for these robots to gain our trust, we expect them to have a sense of ethical norms and to follow certain ethical guidelines. And this isn't a hypothetical question. So in Japan, for example, they're expecting a shortage of 1 million home caregivers by the year 2025. And in Japan in particular is where a lot of work happens on assistive robots. I'm just listing here some of the companies that are developing robots for such environments. Beyond the elder care home, you have, for example, sex robots. Obviously there are questions of ethical behavior, whereas this is, for example, there was this shop that focuses mainly on human-computer interaction for sex robots. There are also in the scholarly literature works and inquiries of designing virtuous sex robots, right? So trying to see whether different ethical theories can apply in particular settings. And we don't have actually to go that far. Even if we look at a just what we might think of as a really just an engineering application, delivery drones, ethical questions arise. So ethically laden questions arise. For example, if the engine of this thing fails and it needs to land and it still has some control capability, it must decide where to land. Does it land in the school playground that's under it? Does it land in a park, etc.? Those, although not on the surface ethical questions, are ethically laden, meaning they have ethical consequences. So when we talk about ethics, what do we mean, right? This is where we make the switch to engineering, if you will, right? What do we mean by ethical guidelines? In my work, I focus on 3 types of statements, right? We look at statements of obligation. So the nurse robot ought to help the patient in greater pain. Permission statements. The robot is permitted to ignore a patient if its battery is near depleted, because presumably there's nothing it can do for the patient anyway. Prohibition. The robot is forbidden from ignoring the patient's symptoms or from taking certain factors into account. So those are the types of statements that I study. They have a certain form, the form of an obligation, a permission, or a prohibition, or OPP for short. And in a longer talk, I would have walked you through, okay, how do we go from these abstract concepts of ethics down to the level where we can do computation. Here, I'm just delivering the final result, if you will. We will be looking at these three types of statements: obligation, permission, prohibition. And in this talk, I will just say obligations, right? With the understanding that permissions and prohibitions are included in that. And part of the solution is to scientifically, which is to say empirically and theoretically, test hypotheses about ethical guidelines. We want to study the logic of these statements. For example, here's what I mean by that, if a formal logic is not in your technical background. If you have an obligation, if there's an obligation that if someone is sick, you treat them, and someone is indeed sick, can I then automatically derive that, okay, well, then I have an obligation to treat, right? Intuitively, yes. The question is, if I formalize these statements, is this something that can be derived automatically, mathematically? If there's an obligation to do two things, A and B, right? Is this the same thing as saying I actually have two separate obligations, an obligation to A and an obligation to B? And maybe I can then assign each obligation to a different agent if that's allowed by the environment. So this is what I mean by the logic of these statements. What can I derive automatically from a set of premises and a set of inference rules? So when I talk about reasoning here, I'm not talking about theorem proving. I'm talking about verification, control, and learning, right? Now, so what specification logics should we use? In system design, we are very familiar with some of these logics. So linear time logic, right? Starting with the work of Pnueli and Zohar Mana. And then a lot of variations on top of that: metric temporal logic, signal temporal logic, game logics, bounded bandwidth, STL, etc. What all of these commonly used logics have in common is that they belong to a family called the family of alethic logics, from the Greek word aletheia, for truth. Alethic logics, it's the logic of necessity, right? It specifically formalizes a type of statement which expresses what is necessary, so always this thing, or necessarily this thing, and what is possible, sometimes this thing, or possibly A, right? That's the form of statements that alethic logics try to formalize and reason about. So we have to ask, well, then how do I say it in English? Do I say the car should never collide, or the car will never collide? Right? There's a difference in emphasis. There's a nuance between these two. Should is an obligation statement. It's a normative statement. It tells you what things should be. Will is a necessity statement. It tells you what will be the case, regardless of what ought to be the case. Now, this might sound like some kind of obtuse distinction. So does it matter? Does it matter whether I say should or will for the way I'm going to formalize things and for the way I'm going to design my system? So why not formalize, since these logics I mentioned are very commonly used, we understand them fairly well, there's a lot of work on them, a lot of tools for them. Why not formalize the car should respect the speed limit as always respect the speed limit? This is what I've done in a lot of my previous work, etc. Well, the problem here is that in those logics I just mentioned, if you say always are, that implies are. That's one of the inference rules. If something is necessary, then it is true, right? If you use always to formalize obligation, you read this inference as, if R is obligatory, then it is true. Now that is problematic because obligations are regularly violated. If you use a logic that supports always R implies R, so if R is obligatory, then it is true, then you're saying all obligations are always met, which is at which point you just go home and, cash in. So this inference rule is not appropriate for obligations. Now, there's a number of other examples I could give from the literature. This isn't mine, right? But in the interest of time, I'll just leave you with this, with the hope that I've at least made it plausible for you that the logic of obligation is not the logic of necessity. We need a different kind of logic to reason about obligations, permissions, and prohibitions. Those of you who are into this and are aware of the Anderson-Kanger reduction know that there is a proposal to turn the logic of obligation into a logic of necessity, but we won't get into that here. So let's introduce an obligation operator. This circle with a dot in the middle is the ought operator. The agent ought to do R. And so from there, for example, if you want to define permission, permission is the dual of obligation in the way that possibility is the dual of necessity. So the agent is permitted to do R is defined as it is not the case that the agent ought to do not R, right? And so on and so forth. There are logics, deontic logics. So a logic of obligation is known as a deontic logic. There are deontic logics where there are different kinds of permissions, but we won't get into that. Okay, so
I'm sorry, could you go back to the previous slide? Just wanted to get my head around the permitted operator.
Mm-hmm.
So it says not obligated to not do R.
Yeah, so there's no obligation to do not R, which means you are permitted to do R, right?
Got it. Okay, yes.
And the way that eventually R means it is not the case that always not R.
Got it, yeah, thank you.
So if you're with me so far that, okay, we need to use a different kind of logic, a deontic logic, well, a bunch of questions naturally arise, which is what I've been looking at the last 3 years. Which logic should we use? In the same way that there is a zoo of alethic logics, there is a zoo of deontic logics. And deontic logicians seem to disagree on almost everything. Which is not a diss. I mean, it gets complicated. So which logic should we use? Can we see it used? Are its problems, its computational problems, decidable? If they are decidable, are they computationally affordable? Complexity. Can we learn obligations in this logic? Because you want to know, okay, well, what are the ethical guidelines that are followed in a particular community? How is this general guideline locally implemented and locally colored? And can we generate all obligations of a given system? And I will spend most of the remainder of the time on that last question, because this is the most recent work we did. But as a sneak preview of everything, I don't know why it says, so which logic? We started with a logic called dominance act utilitarianism, which I'll describe, and then we modified it along the way. And I say stay tuned because we keep modifying it to make it more applicable to actual robotic systems in deployment today. Can we see it used? Sure, in a longer presentation, but we used it, for example, to formalize a proposal from Intel known as responsibility sensitive safety. Are its problems decidable? We looked at model checking. It is decidable. Are they computationally affordable? So we did implement the model checker, and it's linear in the size of the transition system that you use to model the robot, exponential in the size of the formula. Can we learn obligations in this logic? Yes, we can, under, in a particular way. And can we generate all obligations? This is what we're going to look at. Any questions so far?
Yeah, are there any open questions?
Sorry, there's a question in the chat, but Christoph, you can go ahead.
Oh yeah, just said, yeah, I mean, you have a check mark everywhere. I guess maybe you'll come back later. I hope there's some open questions.
Sure. So Ali, isn't the logic of necessity equivalent to the logic of prohibition? No, my contention is no. I gave an example of why that is, right? And maybe in the Q&A, or if time allows, I'll actually give us, hey, let's model this particular situation, and how would you want to model it in the logic of necessity? And I will argue that none of these are actually adequate, and I'll explain why I think so.
Okay, thank you.
Thank you. So this operator, the circle with a dot in it, is the ought operator from dominance act utilitarianism, which is a deontic logic developed by John Horty in 2001. And the way to read this formula is agent alpha ought to see to it, so ought to ensure that some state of affairs A is true. And we use CTL star to describe states of affairs in the world. The window is open. There's a future in which the window is open, etc. Right? But you can use something else. So this is how to read this. Agent alpha ought to see to it that A is true. And the semantics are actually utilitarian semantics. That's why it's called dominance act utilitarianism, which is nice because we can connect it pretty quickly to things like reinforcement learning or model predictive control, just maximizing an objective function. So if at a moment M, the agent has two actions available, stay in its lane, change lanes, it's branching time, so there's non-determinism. If it stays in its lane, the future could evolve in two different ways, H1 and H2. If it changes lanes, the future could evolve according to H3 or H4. And each one of these histories has a value associated with it. So you can think of this as the expected long time utility of following this history. Of course, there are future actions along the histories which are not shown. So quite simply, what is the agent's obligation? The agent's obligation is to pick the action which dominates all other actions. And dominance here in this original logic is defined pretty strongly. So stay in lane dominates change lanes because the worst action, the least useful action, the worst history here still has a utility which is larger than the best history here. So 9 is the worst history here, and it's that 9 is larger than 3, which is the highest value here. And so we say basically the agent's obligation is to see to it that A, because A is satisfied by all histories in the dominant action. So A is a necessary condition for this ideal state of affairs. So in a nutshell, the agent will always take the action, or should, we don't know what it will do, but it should take the action that dominates all other actions. So it's utilitarian and dominance act utilitarianism. Now this logic already allows us to distinguish in the logic between 4 different concepts, which is important for us. It models ability, who can bring about A. You can bring about something but not actually do it. Agency, who is actually ensuring A. Obligation, who ought to bring about A, who has the obligation to ensure A. And necessity, so it also includes an elliptic logic within. What will be the case? In elliptic logic, you can't really distinguish between these 4 things unless you jump through some hoops in your atomic propositions. But here, these are in the logic, and so you can reason about them in the logic, right? You can reason about agent alpha has the obligation, but it is actually agent beta that met the obligation, etc., etc. So
there's a related question in here. The question is, can you mesh the 2 logics used both in a single equation? And by 2, I guess I mean elliptic and deontic.
Yes, and this is what DAU does. So because to describe the state of affairs, to say alpha ought to see to it that the window is open. I'm going to stick with this example, right? The window is open, that's described in an elliptic logic. The window is always open, for example, right? And DAU, dominance act utilitarianism, adds the deontic layer, adds the obligation layer on top of that.
Yeah, got it.
So I'll just give a simple, okay, why did we go through all that effort? Because now we can reason about obligations. So we, for example, in this logic, it supports the validity that if alpha ought to see to it that A, then it can see to it that A. I'm not gonna hang on the symbols, this is just for ability. So ought implies can. Why is this? Doesn't mean you will. What you will is up to your controller. But if you have an obligation to see to it that A, then you can. What's the point of this validity? Why is this something that actually is useful? because it prevents you as a system designer from putting obligations on your agent that it cannot meet, which would be useless. So through the logic, you can, it doesn't allow you to put impossible obligations on your agent, at least not by design. And then, we looked at all sorts of implications and so on and so forth to see whether we agree with this logic. And then now that was Horty's logic. We extended it because we're looking at MDPs, Markov decision processes. So, we added probabilities on the histories. We saw that we preserve the validities that we care about, et cetera, et cetera. We created a model checker for it. If you have a finite transition system, we can model check it against a DAU or EAU formula with certain complexity. And here I will focus on, can we generate all obligations of a given system? What do I mean by that? So you have a reward function. You have an MDP, and it has a bazillion states, and you ran reinforcement learning, you computed the optimal policy, or you approximated the optimal policy, and you have these rewards. And maybe actually your rewards came from inverse reinforcement learning, right? So you place these state-based rewards. So you know what it's going to do from step to step, but what does this say about its obligations? What is the agent trying to do in a language that we understand and which is still amenable to algorithmic treatment? Can you describe in a succinct way, the agent ought to do this, or the agent is trying, the agent has as objective to bring about A, as a global description of the agent's behavior, rather than as a state-based reward description, or even as a policy. More generally, given a controller, what is it really trying to do? A modern control system will have a bunch of control loops running on board at different levels of the control hierarchy, etc. Right? There is an emergent set of obligations from that, right? So you can look at each control loop and say, well, here's what this one is optimizing for, and here's what that one is optimizing for, and here's what this one is optimizing for. But put all together, what are they all together optimizing for? What are they all trying to do? And so by asking these questions, I formalize it as, given a control law, the set of control laws, what are the obligations of this system? What does it think are its obligations? Because that gives me a way to understand or to better predict its behavior, right? And this isn't a purely pie in the sky question. This isn't a theoretical question. In 2016, Mercedes had just decided that, okay, they will be programmed, its self-driving cars will be programmed, well, it's highly automated cars, will be programmed to sacrifice pedestrians to save the driver. Shortly afterwards, they recanted, so to speak, and meaning that they said, okay, there is no instance in which this actually happened, and that's no longer the case, right? So in this case, Mercedes sort of programmed that in. What worries me is the behavior that is not explicitly programmed in, but does emerge overall from the system. So we can generate, actually, it's fairly simple to generate all possible obligations from a finite transition system. If you know what are the atoms of interest, you put them on the states and you just run through it, right? It's an enumeration problem from hell. Just enumerate all obligations of length 1, all obligations of length 2, all obligations of length 3, on and on and on and on. So, okay, we can do that. But you can probably suspect that most of these are not going to be interesting. You don't want to do that, right? Because you're going to, the system ought to start from the initial state. It's like, no kidding. Okay, that's not interesting. What you want to do is generate obligations that are interesting to the system designer. Now, what the system designer deems interesting is up to her. Maybe, oh, wait, why does the system think it ought to change lanes twice in a row every time, right? Why does the nurse robot think it ought to just stand outside this particular patient's door, etc.? So perhaps interesting means surprising, but that's up to the designer. This is what we want to do. So the way Colin, my student, went about doing that is to say, okay, I'm going to generate, imagine, if you'll grant me this initial box, generate an obligation. have the designer score it according to their interest in it. Update a model of interest. So we are in the loop, we are updating, learning what this particular designer thinks is interesting. And then with that, we go back and we generate a hopefully more interesting obligation, etc. So there's a loop here. And finally, once you've learned, once you've converged in your learning, you generate interesting formulas that are valid of this particular model. Meaning, so these are obligation statements that are valid for this model and which the designer deems interesting. And that is basically like a debugging aid. Of course, we can run this in a community of people, say, hey, okay, Google is about to, deploy their cars here. Do you want to know what their obligations are, what their permissions are, perhaps even more interesting, right? What they think they are permitted to do. One level deeper in the technical side, the model of interest is basically a Gaussian process with a string kernel, right? Because what are we learning here? We are learning to map a string, right? When you write out the formula, that's a string, to a level of interest. So the search is happening over a string space. We reuse the work. Okay, the citation is late in coming. So anyway, we reuse a tool called BOSS, which created Gaussian processes over string spaces. And okay, how do we bootstrap this whole thing? We just generate 5 random formulas, get their interest levels from the designer, initialize the Gaussian process with that, and then we start looping around, hopefully until we get a good model of the designer's interest, and then we start generating interesting valid formulas. So it's an interactive process. It can be labor intensive, but in initial experiments, we'll see some of the results. Initially, we allowed the generation of non-valid formulas, meaning formulas syntactically correct, but they're not true of this model. Why? Because they might be a part of a larger formula, which is true of the model. So we don't have a very good handle on this, honestly. But this is what Colin has running right now. And by the way, when I say the formula is true of the model, so alpha ought to do A, this doesn't mean that the model actually does A. It simply means that the model has an obligation to do A. The model's objective is to do A. What it actually does, again, is up to the controller. So this is reward design, if you want to think of it in these terms, or reward verification. But the reward here is global. So this is from fairly small experiments. Here you have the event. So every point here is a formula, is an obligation statement. On the x-axis is the score that the evaluator, that the designer assigns to it. So think of this as ground truth. And on the y-axis is the interest score that the model, the Gaussian process, assigns to it. So higher is better. So on both axes. So let's look at just randomly generated formulas without running the loop, right? Just generate a bunch of random valid formulas. Where the evaluator scores them, this is a particular evaluator. Yeah, I think this is a particular evaluator. We should have results for like average of evaluators, but I'm not sure that the average of evaluators makes sense because different people think different things are interesting. So for the randomly generated formulas, most of them score pretty low, except for this one. Well, let's say from 0 to 60 with most of them at 0. The model also scores them fairly low, right? For the optimized formulas, meaning the formulas that are generated after we've learned the Gaussian process and now we're generating what the model thinks are interesting formulas. Okay, you have a spread with a cluster over here between 60 and 100. And correspondingly, the model thinks similar rather. So starts from 50 to 100 with this cluster here. So this here is where you find false positives for the model. So things that the model thinks are interesting, but which the designer disagrees with. And these are the false negatives. Things that the model thinks are uninteresting, but the designer thinks are interesting. And so we have a nice cluster here, but obviously with data points all along the spectrum.
Sam, there's a question on like what is the context in which these are generated? You can see it in the chat, the question if you want.
So, right, so the setup for these experiments, and I have some backup slides about it. So Colin created an automaton, like a very simple automaton for a grid world where the automaton does reach avoid. It wants to get somewhere and avoid lava, I think, right? And so Colin described, so Colin described or showed the action of the automaton to some, students in my lab, basically. So, technical people. And then he started showing them formulas. Oh, the automaton ought to avoid the lava. Uninteresting. The automaton ought to walk along the lava. Okay, that's interesting. Why would it want to do that, etc. And so this is how he collected each designer's interest level in various formulas. Now, I think you had something about context in the question.
Yeah, so
yes.
What I mean is, maybe you don't want to walk the lava. So the example I had there was change in state. So in state 1, I'm hungry. So I should make dinner. I ought to make dinner.
You as the designer, or you playing the role of the agent, like the automaton?
Agent. State 2, I'm not hungry. I have no obligation to make dinner anymore.
Right. So the logic does support conditional statements of the sort. I ought to make dinner if the family is hungry.
Okay.
Yeah, I didn't show them, but it does have that condition, the ability to condition on states of the world. In these particular experiments, the grammar allows it. So I don't know if he actually generated conditional statements or not, but the grammar allows it.
Okay, cool.
Yeah. And so looking at the same data a different way, this is the evaluator score, higher is better. This is a histogram of the scores of the optimized formulas. This is a histogram of the scores of the just randomly generated formulas. And the difference between their averages is 53, which is more than half the range of interest here. So we have like a nice separation. But again, I would want to run this on a much larger, but that's stuck in the IRB process. So I could do it on my students, but not on the general population until we get the IRB approval. That's it. So as a summary, use an expressive verification and control friendly deontic logic, DAU, extend it with probability. We're extending it with other stuff right now with Kendria. We can use automated reasoning to derive undesirable consequences, which we did actually for the RSS proposal. Undesirable meaning, okay, here's a seemingly good principle. We like this principle, but if you run it through the logic and you formalize it around the logic, it turns out it also allows this other thing, which is not so good. So you want to do then refine your design, etc. Can be model checked and learned, can be generated in an interactive setting. Acknowledge the NSF's support for this work. And with that, I would like to open it for Q&A.
Thank you, Sam.
Thanks, Josh.
If you have any questions.
And actually, I want to line up this other example I had for this one.
Yeah, I mean, I had a question about examples, like for the RSS one, what were the kind of interesting cases that you found that maybe could formalize, but they did not make sense from a point of view of it shouldn't be done, for example?
So for RSS, basically this is from Intel/Mobileye, a set of rules or guidelines for what self-driving or how self-driving cars ought to behave. So they call it RSS. There is that obligation language in there, right? A car that drives at the opposite direction to the lane direction should brake harder. We might reach contradictions. On the one hand, we should accelerate, etc. Should. Okay. So one of the premises is that a car, such as this rectangle here in the middle, simply needs to worry about its interactions with the other cars, right? So I worry about interaction with these 4 cars around me. I do not worry. I don't have to worry. I'm permitted to not worry about how my behavior might imply behavior between 2 other cars. For example, if I keep hitting the brakes on the highway, I don't need to worry whether that forces the 2 cars behind me to get into an accident, because the guy behind me is also hitting the brakes repeatedly and he gets into an accident, right? Or she gets into an accident. So they call this star calculation. It's a way to reduce the complexity, basically, right? Just worry about one-on-one interactions, not two-on-one interactions. So I thought, okay, let's formalize that and see what it says, because it felt a bit wrong. Like, surely you have a responsibility not to do something that causes an accident between 2 other people. So we formalized it, and this is one formalization. And my slides are jumbled up. So I can go into this, but basically the upshot is that this here, you can think of this formula as a formalization of the star calculation. So all of it, all together, it says alpha ensures, alpha is the agent, that it does not refrain from facilitating the accident. So facilitating the accident is bad. You don't want to do that. To refrain from facilitating the accident is formalized like this. And if you're permitted to not refrain from facilitating the accident, this is what you get. According to the logic, this is actually equivalent to alpha deliberately sees to it that this accident between the 2 other cars happened. So this is a case where we formalize a principle of RSS and you run it through the logic. This turns out to be equivalent to alpha deliberately sees to it that this accident phi between 2 other cars happens. So I'm presenting it here without the obligation operators, just to not make it look even longer. But so this is an example of what formalizing can give you. So it was a nice experiment, basically.
Cool. I mean, someone could argue that this is just a byproduct of the way you're formalizing it and not so much the intention of the rules. How do you get around that?
Right. So I can't read into people's minds. I'm sure that's not what they intended, right? And yes, if someone comes in and formalizes it differently, they might derive something else from it. So there are certainly 2 players here. There is the original principle as expressed in English, and there is the person formalizing it. Now, I can argue that this is a legitimate formalization, right?
Sure, yeah.
Yeah, so.
Cool. Christoph has a question. He has a hand raised. Go ahead, Christoph.
All right. Yeah, thanks a lot for the talk. I'm assuming maybe you've seen recent work from Chris Gerdes on formalizing duties, and sort of, I guess, it's a way to come up with a set of principles that engineers could use to make decisions about what safety means with respect to, particularly with respect to legal principles, right? And so, like, it seems like this would be a very good fit for deontic logic. And you also mentioned at some point, I guess it was for the RSS formalization, that you use a form of deontic logic that has this utilitarian perspective. I kind of just wonder, I mean, it's a utilitarian perspective, sort of general principle, or because, like, let's say I think, well, the whole idea in formalizing duty to other agents is that this trumps, trying to basically compute some kind of a global utility and make these decisions that are essentially often, like, impossible, or give you get you into contradictions, like, the trolley problem, basically, right?
Right.
So basically, I think, from at least, how I understood the points that Chris Gerda is making is that, yeah, we should formalize more the duty to individuals and what principles we would apply, as opposed to trying to be, utilitarian and try to have some kind of general tally of benefits.
Right.
So I wonder whether you've been thinking about this and how this fits into deontic logic. Is, like, does this mean that certain deontic logic would be more appropriate than another? Yeah, just wondering about your thoughts.
So the work of Chris Gerdes that I'm most familiar with which is some of his early work in this domain, where he looks to design objective functions for controllers to ensure safety, well, mainly to ensure safety and other, let's say, desirable properties. So that is still very much in the, that work that I've seen does not express things.
Yeah, that's not the work. I mean, he basically, it's the latest work. He just published a paper. He worked with Ford on this. And it's, it's sort of like, I think, well, he was a contract for, like, to kind of look into ethics and difficult decision-making. And that's what they came up with, which is essentially, libertarian rather than utilitarian perspective. And they basically trace it all to legal frameworks, like, let's say, in the US.
So the question there, so you're right, this particularly on the question of the utilitarian principle versus a deontic non-utilitarian approach, which is actually typically also in philosophy, the two are actually opposed. So this particular logic is a little bit odd in the sense that it is a deontic logic, but which is based on utilitarian principles. The question to me as a system designer or system verification engineer is, whatever logic I adopt, ultimately, if I want to verify it against the system, if I want to create controllers to enforce those deontic obligations on the system, ultimately that has to somehow be boiled down algorithmically to calculation and that the controller takes into account, or that the model checker performs. So I don't think there's any avoiding some type of, let's say, reward, right? It might not be a global utility function, but some type
That's
of
right. Yeah, so it's going to be per agent, with respect to the duty to the agent that one has, as opposed to, like, maximizing welfare, right? Yeah, I see. So is that, let's say, in the logic that you use to formalize RSS, and it was a little bit quick.
Yeah, sorry.
When you briefly introduced that, I mean, the utilities are do you have utilities per agent? I mean, it's sort of in a game theoretic sense, or?
Excellent question. All of them were excellent questions. So the DAU, as originally formulated, it can account for multiple agents, but it makes this very strong assumption that all agents agree on the value of a given history. So these are think of them as cooperative agents, and all of the agents, which I'm not showing here, agree that history H1 has value 3, whereas history H4 has value 9, right? And so if you just want to take that and apply it, what you would have to do is come up with, like, the product automaton of all the automata. This is how you're modeling your agents. And the way we compute an entire history's value right now is just the expected long-term cost. If the agents do not agree, this is something that my other student has now looking at. It's like, what does that do to the logic? Because there are some features of the logic I want to preserve and for which I am using it, right? Some validities in the logic that allow me to do reasoning. Now, if I give up on the assumption that all agents agree on the history values, which is more realistic, what is the logic of such a setting? What is the logic of utilitarianism in such a setting, right? And I don't have an answer for that because we just started.
Right, yeah, that's interesting. Thank you.
Thank you.
Okay, I don't see any raised hands. Yeah, so I do have one more question. So you've used this for, I guess you can use this for verification. You already have your methods for that? Have you also come up with methods for synthesis that is given a set of obligations? No. Okay.
Right. No, not yet. And the synthesis. Well, I'm looking for the student who will jump on that. The synthesis problem is a bit frustrating for DAU because so the agent ought to do the maximum, the dominant action, right? So if you know what a dominant action is, just do it and problem solved, right?
Mm-hmm.
Something feels odd about that to me. Something feels odd. I'm missing something. So I haven't started looking rigorously at the synthesis problem.
Okay, cool. Anyway, I think we should talk more about that because Soroush is working, for example, on synthesis for LTL specifications, but there are some concepts that he's exploring there which might be useful here.
Yeah. One nuance here is LTL, for example, is the objective, and you develop a controller to meet the objective. Perhaps perhaps the correct synthesis problem for this deontic logic is, how do I design the system, the plant, not the controller? How to design the plant so that it has this obligation, so that this is its objective, and then Soroush can develop the controller that enforces the objective. So it's two levels of design, right? I think with DAU or deontic, you design the plant and then to have certain objectives, and then you bring a controller that meets the objectives.
Got it. Yeah.
Yeah.
Christoph, do you have a question? I see a raised hand.
Yeah. I was just wondering, is there a relationship between like default logics and deontic logics, in the sense that you could treat obligations as kind of defaults, where maybe in some cases you specify exceptions.
Yeah.
But if nothing is stated, then basically the obligation is a default, right?
Yeah. There is a line of work that I have skimmed that uses defaults in deontic logic, especially when you start thinking about what happens if the obligation is violated. What should you do next? Because if you fail your mission to go to the next office, you just fail your mission, and that's what's up. But if you violate an obligation, in a sense, you expect some kind of repair, right? Okay, you have to make things good because it's an ethical obligation or something. So I'm aware of a line of work there. I'm happy to send some links, but I haven't really delved into it.
Yeah, it's still kind of trying to see, like, let's say there should be a way to talk about, well, I guess it would be the difference between necessity and an obligation, and I guess assessing the probability that the obligation will not be met. Because I mean, like, yeah, I guess as a designer, I would like to be able to talk about that, right? And, or like analyze, what's the probability that my obligation will not be met. And then, of course, I want to understand whether it's the, I mean, it's a sort of pure omission from the system. But I guess, a system cannot be forced to do an omission. Like if a system is forced into a certain situation, the obligation is really just something about what the system decides, what it has control over.
Yeah.
Is that right?
Yeah. Did you say you can't force a system to omit something?
Yeah, I guess probably not, right? I mean, because like, I guess if you say the system ought to do something, like at least in theory, it should be, if the system is well designed, it would be, let's say, fulfilling its obligations. I still like, what are good examples where, let's say, you really need to make this distinction
between
and you actually have to work with obligations. I mean, you touch on these things. I understand this was like core of your talk, and I like everything made perfect sense.
So here's where Here's a perhaps more
but I always think that, like, okay, well, I mean, I could go and express it, you know, just in real logic by just additional, with some additional, I guess, predicates or whatever.
Right, exactly. That's the thing. You would have to bake it into the predicates, right? And how do you then reason about, like, if you say A and B, that's just A and B. But if A is in the logic an obligation and B is in the logic a permission, then the logical machinery allows you to infer things from it. If, however, you bake the obligation or the permission into the atom, there's nowhere else to go from A and B, right? That's it. And that becomes particularly important. And as long as you're meeting all your obligations, then more power to you, right? You don't have to. Where it becomes important, I think, is when you want, let's suppose you ought to drive slow and you don't drive slow, right? If you want to express that in alethic or like just propositional logic, that's drive slow and not drive slow, which is false, like equals false, end of story. But you want to be able to actually infer something from that. I ought to drive slow. I didn't drive slow. Therefore, I ought to what?
Right. But is this? I mean, is this the idea is that you're admitting this possibility that the obligation is not met. Mm-hmm. Like I can imagine in the logic probably it doesn't matter, but let's say in practical application, what is the reason for why the obligation is not met? I mean, are we allowing a reason being that the system is not perfect, or are we allowing that maybe the system is now in some kind of an open world? Well, I guess it's sort of similar, right? And we haven't accounted for the situation, right?
Yeah, or the system is poorly designed. Not poorly designed, but things escape the verification stage. So all of the above, basically.
Right. So then maybe like let's say your mining that you presented, the example of mining for interesting formulas. I mean, how is that different from, let's say, like mining probabilistic statements? Like what would happen? Like what the system would do, right? Like, for example, you said that, okay, well, like maybe the vehicle tends to change the lanes. Like always, do two lane changes in sequence or whatever. I guess it was one of the examples you mentioned.
Right.
I mean, I could treat this as a probabilistic statement and say, this will be observing that the system is doing this. And under some assumptions about the real world, I could derive that the system will do this under those assumptions. And if I put some probabilities on the assumptions, I can then say, well, probabilistically, the system tends to do that, right? And how would that be different from the inference that you do?
If I followed correctly, I think those are two different inferences. The first one, by the way, we did this with a probabilistic variation on, we call it EAU for expected. So the statements themselves are in PCTL, right? Probabilistic CTL. So we take that into account. But back to your question, if I followed, one is you're observing, or maybe you're not observing any traces, you're just analyzing your system and you're saying, this will do two lane changes with probability 0.9. And versus the other one, which says, this agent thinks it ought to do lane changes at least 90% of the time. Is that the question? Like, what's the difference between these two statements?
Yeah. I mean, like, what's the bottom line for a practitioner? How these two, like, I mean, like, is there something actionable that, like, I could get the insight from a probabilistic model checker versus that just uses
I think, well, so
logic of necessity,
right
versus this.
So the second statement with the obligation in it is saying your optimal policy in this particular setup, which has an MDP, etc. It's saying your optimal policy guarantees that you do two-lane changes with probability 0.9. That is not necessarily the case for any policy. So when you say
Oh, I see. Yeah.
Right? And so it depends on what actually happens in practice, depends on the policy you deploy. This is making a statement about the optimal policy.
I see. So it's basically, yeah, because you were saying you're deriving this from the reward function.
Right.
Yeah. Okay.
Thank you.
Thanks.